Adversarial Branch Architecture Search for Unsupervised Domain Adaptation. I'm Luca Robbiano, and in this video I'm going to show the main concepts of this paper. The cost of manual data annotation has led to the development of techniques to employ deep learning models within domains where few or no labels are available. Unsupervised domain adaptation methods transfer knowledge from a labeled source domain to a target domain, where only unlabeled samples are available. At the same time, the growing demand for better performing models led to higher interest in neural architecture search, which aims to automatically design neural models without the need for a long trial and error process by experts. Combining unsupervised domain adaptation and neural architecture search is a challenging task, since most UDA methods require a pre-trained backbone to be competitive, and an AES cannot exploit ImageNet pre-training. However, a class of domain adaptation techniques employ a dual-branch architecture, with a pre-trained backbone and a second branch that performs some task to adapt it to the target domain. In adversarial methods, the secondary branch tries to learn to distinguish source and target domains, while the backbone attempts to fool it. Since the auxiliary branch is trained from scratch, it is possible to optimize its architecture while keeping the pre-trained backbone. Another issue in combining neural architecture search and unsupervised domain adaptation is that not knowing target labels, we cannot measure the accuracy on target, which is what we are interested in maximizing. So we need a way to compare different candidate architecture and select which one is the best on target, without actually evaluating it. This model selection problem is actually double. We need to select the best epoch on target within a training, but we also need to compare the performance of different architectures, without target labels. There is no consensus within the domain adaptation community on how to solve this problem. Several approaches have been proposed to define metrics that correlate well with the target accuracy, without needing target labels. For example, one could minimize the entropy on target, or measure how much source and target features are well clustered. However, several metrics might encode complementary information, and choosing one might lead to a loss of information. This plot shows several models. Each axis represents a performance metric, while the color represents the actual performance on target. Flattening all the points to a single dimension would make it harder to distinguish between good and bad models. We propose an ensemble model selection method. We use a linear regression model to predict a value that will act as a target accuracy proxy. Since we don't have target labels, we cannot fit this regressor using target accuracy as ground truth. For this reason, we propose using another dataset for which we do have target labels. We can fit the EMS estimator on this auxiliary dataset and then transfer it to our dataset of interest. We randomly sample many models which we train on the secondary dataset. We use their matrix and their known target accuracy to fit the linear regressor, and then we use the same regressor to predict a score for a model trained on our dataset of interest. Our experiments show how an EMS estimator built upon 6 metrics outperforms each one of them in terms of correlation with the actual target accuracy. To optimize the branch architecture, we propose ABAS, built upon EMS and a Bayesian optimization algorithm, BOHB. Our pipeline works by proposing a branch, training the resulting network and estimating its performance on target through EMS. The EMS score is then used by the BOHB algorithm to propose new candidate branches. In our experiments, we applied ABAS on two adversarial UDA methods, DANN and the more recent ALDA, consistently improving their performance on 3 datasets, Office 31, Office Home, and PACS. In conclusion, we propose a data-driven ensemble strategy for model selection in UDA. We show the importance of the auxiliary branch architecture and build a pipeline which is, to the best of our knowledge, the first fully automated branch optimization pipeline for UDA.